Okay, so today I'm going to present Rethink Energy Accounting with Cooperative Game Theory. So this paper is one of those classic examples which borrows some established concepts in one field and applies it to the other, and do some interdisciplinary research. So what is energy accounting and by a software? It's actually a measure of energy consumption attributed to software principles. And what software principles could be different kind of software applications, threads, processes. And why we do energy accounting is based on energy accounting of software. You can evaluate a software and you can also do different sorts of energy management in operating system. um, they have given this example of iPhone teardown, and in which they saw that there are currently a lot of resources, hardware resources, which the system uses, and it's very hard to attribute the energy consumed by each of these resources to individual software principles or applications. And currently, the state of the art in this field of energy accounting is this policy 5. uh, there is a problem in there is a thing in energy accounting that there is no ground truth. Whatever has been proposed previously, like from policy 1 to 5, they cannot be compared to some sort of ground truth because it's very hard to predict, and so they are being evaluated quantitatively. Okay, so what policy 5 is it does is it takes individual software principles and assign the energy from different components in the hardware resources. In this equation, you can see that x1, xp are called predictors. What they really are, they are different kind of hardware resources and how they are contributing to the overall energy of any software principle. And this equation is linear, as you can see, and there are totally n principles that contribute to the predictors. In this matrix, you can see that uh, the columns, if you see one column, that's like a column vector that contributes to one software principle, and if you combine all, then that's the total energy consumption of the entire system. As you can see in the last equation, that energy contribution by a principal I, which is one software principal, is the column vector in the above matrix. The problem with this policy is that we can only use those predictors, those hardware resources which are software visible. For example, CPU cycles, amount of data and memory usage, etc. But we cannot take into account those hardware resources which are not visible to the software. Hence, we cannot properly quantify all the hardware resources available and contributing to the energy of that particular software principle. And plus, it's practically infeasible to account for all the hardware resources present, as you can see in the previous slides of the iPhone. And the second problem is that model must not be linear. It can be problematic because different hardware resources does not impact the energy in a linear fashion. It's mostly non-linear. So linear does not capture the proper aspect of energy consumption. And the third problem is that this constant factor B naught, it's hard to attribute. B naught is actually the residual energy left after attributing different kind of energy to different hardware resources. So there's just no way to attribute this constant factor to any software, to any hardware resource. There's no way to quantify it. These problems are fundamental, and I've already mentioned we don't really have a ground truth. So what the authors in this paper, they say that energy consumption uh, uh, through a software principle, they can model it as a cooperative game, and they can prove it to be the ground truth, but only theoretically, not practically. So what is a cooperative game? This is a concept derived from economics, and what cooperative game theory is, to see how much of the surplus, how much of the amount that can be divided among the contributing players. Shapley has taken this problem and he has devised a Shapley value which
anyone knows anything interesting about this guy?
He's
exactly.
Yeah.
He's a professor here at UC.
Is or
Yes.
is or was?
Huh? Is.
Is.
Of course, in like late 80s or something. He is.
He's still here. Okay.
Professors don't have retirement age.
Okay. So the problem is that this information which you can currently see, it's not sufficient to find the to find the amount of surplus that is contributed to each of the player. We need more information according to Shapley, and the information is this: we need all the possible subsets of the different contributing players. If there are like 3 players contributing, then 2 power 3, 8 combinations, 8 subsets you need to account to calculate the Shapley value. And this is the Shapley value. If you can see what this is this is the amount of surplus for this one player, and how it's calculated is that it's iterated. It's like a marginal energy or marginal distribution of that surplus amount over all possible sequences. This is the Shapley value, and what the authors argue is that this Shapley value is the exact measure of the energy consumption of an individual application or a process. As you can see in the numerator part, this is like the marginal marginal surplus distribution, and what it says is that if you want to have if you want to know the surplus of one player, you have to take a set which has that player and then subtract the set which doesn't have that player, and the difference will give you the amount of the surplus of that player. So there are 4 axioms which Shapley value has to conform to. Number 1 is efficiency, and these axioms are quite intuitive, which is like all the players' individual surplus should equal the total surplus. This is the efficiency. The other is symmetry, like if replacing one player with the other have a same impact on the total surplus, then they both are the same. And null player is that if you add or delete that player, it does not contribute to the distribution of the surplus. It has no effect on the distribution of the surplus. And finally, the additivity, which is also like the linear property. It's like in 2 different games, if the player has different surplus in 2 different games, but if you combine those games, the surplus should be the summation of the surplus of the previous 2 games. The same analogy can be done for the energy consumption. If you see that energy consumption is also a cooperative game, then how much energy consumption can each software principal contribute to? So here we have taken these 3 different software principles or applications and how much they contribute to the battery. The same properties hold for that, and they are also quite intuitive. If we say that only these 3 applications at one time contribute to the total energy of the system, then their individual energies should sum up to the total energy. And symmetry is if replacing one with the other does not make any difference to the energy, then they are the same. And if adding a software does not affect the energy consumption, overall energy consumption, then its individual energy consumption is 0. And finally, in a given time period, if you make the slice of the time period, and then the individual energy consumption in one slice should equal to the sum of the energy consumption in all the slices.
So, in what is the information that their system has? In the sense that, like in the linear example, you had the system visible resource usage. is the equivalent out here? What is it that, so system is certainly seeing the energy consumption.
Yes.
It sees what applications are running.
Yes.
But what else does it know? I mean, it has to know something else to be able to apportion.
They have taken a time period and it's pretty small, like a 10 millisecond. What they say is that in that particular time, if they are, for example, taking into account the application of, the energy consumption of 10 applications. So they have sliced the time into very small intervals, and in that small interval, they are sampling for power, for energy, and in that time period, they assume that very small number of applications are running.
Could be one or two different subsets.
Yes.
So they're saying in this time slice,
Yes.
this set of applications.
Yes. They plug all into the equation and then they get the Shapley level. So their 10 millisecond interval is what they say gives them the value. Okay, so if we consider our smartphone and there are so many different applications running at the same time, it's very hard to make all the possible subsets and calculate their energy. It's not practically feasible. So they have proposed, you can also see here, it's only like 3 applications, you have 8 subsets, and if you increase, the subset will increase. So it's not practically feasible to calculate or measure the energy of all different subsets for large number of applications. And also they argue that the energy consumption of a software principal is highly random because it's not a static number. It will vary depending upon different conditions, on different dynamics. For example, and also it depends upon the hardware configuration, as we all know. And then the second point, I mentioned that energy consumption of any subset is not available for all the different subsets. So because you can see here, there is a possibility that some subsets will not occur at all. So they have the solution they give for this is that number one, which I've mentioned, that measure A for short time interval, that also somehow gives a solution for this, that it's not available for many S. And the other thing which is like energy consumption also depends upon the hardware state. So they have extended their energy consumption of a subset and incorporated also the hardware state. I mean, they are also measuring energy of that subset given a particular hardware state.
I mean, I would have thought it would depend upon the software state. Like what I mean by that is, let's say I have an S where, I don't know, YouTube is running and some other thing is running, right? But it also depends upon what is YouTube doing. Maybe it's on pause versus it's actually playing the movie, right? So
it depends what they take as their software principles. If you say that YouTube is running, that's another application that's running, right? Right. But the state is
for the same S. Yes. S is the permutation, right?
Yes.
Right. So for the same S, if let's say application I and J were running, but I and J may be doing different things in the sense, if I sample now and I saw that only I and J were running, maybe I is in state 1 and J is in state 1 prime, and it's okay. Later on when I sample again I saw I and J are running, but now this time around I is in some different state as 2, J is in some different state.
It depends what they're running. For example, they are doing some kind of web-based action, they're playing video or whatever. So that's what they call state. For example, if what is the Wi-Fi state? How is it using that? What is the CPU state? That's the state. That's what they are referring as the hardware state. Okay, and then again the same problem. You cannot actually measure all the possible states. There are some states which will not, I mean, the combination of those subsets and those states will not occur at all. So for those, they will do some kind of estimation based on the ones which they have already observed. Here, what I mentioned is that some states that you will not observe at all, like 2 different kind of applications that cannot run at the same time. So those states, those subsets will not be visible. and what they do is that they approximate those missing states by in a recursive manner, which I'll show in the next slide here. So I've added the slide which they have not added, but okay. So there are two different, they have made a table which is like S cross the number of states, as the number of subsets cross the number of states, and they estimated in the entire table different values of this energy of those subsets given that proper state. So in the entire table, which you can see here, the gray ones, those can be missing. Those particular states may not occur at all, or you cannot measure them. So what they do is that the white ones which they already have, they estimate the gray ones based on what they already have. And they estimate using these equations. As you can see in these equations, how they estimate is that through a linear square regression kind of estimation they are using, and in order to measure one particular row and column, they take all the previous and all the next rows and then find out in the first equation they minimize the error between all of them and find the coefficients, and then in the next equation they use those equations to estimate the unknown state, unknown subset with the state. Okay, these are the equations. And yeah, so what they say is that they are using a lot of approximations in terms of Shapley value. They are approximating the energy within a 10 millisecond time period, and then they are also approximating the missing states. So they have named their approximate game as the policy Shapley value. This is their evaluation board. They have also used Panda board and the external battery and SD card. Their system of estimating different kind of states based on the subsets take a lot of memory. They said that it's like 100 MB in a day, so they store all that data in their external SD card. I mean, I wonder how they can incorporate that in a real mobile device with all that kind of data.
I think they're doing that only for evaluation, right? No.
I mean, if they want to estimate and evaluate all of that, I mean, they would need that in a real system. How else would they estimate all those subsets, energy of those subsets?
No, they do it once, like they do it once on a platform, and then yeah, you're right.
I mean, I don't know if they can be trained one time. Okay, this is their system. They have their two systems. One is the energy measurement system, this one, and the other is energy accounting system. So they are sampling it at 200 hertz, like roughly every 5 milliseconds, and saving that data in the memory. And what this mobile system does is that take that data and then calculate different ES values, do all sort of estimations, and then rate the apps, like which app is consuming the most amount of energy, and like sort them in that way. And now they also have a problem of evaluating their policy, since we already argued that there is no ground truth. The only ground truth that they say is like the theoretical version of the Shapley value, but their scheme is like the approximate version of the Shapley value. But they still did the evaluation. I don't know. Based on the evaluation, they are evaluating against policy 5, and they have kind of considered themselves as the ground truth. That's what I've taken out of the paper. Their approximate version as the ground truth, which is not right. Okay, so they say that their accuracy in terms of the battery interface, which is already in the phone, is 90%, and then they are also able to identify the top energy consumers. Their benchmark applications are download, web, video, game. What download means is that they have grouped different download related applications in download, web related in web, and video in game. And since web, video, and game cannot be played at the same time, so they have 3 different scenarios. In this figure, you can see that S is their Shapley approximate value. It's 100% efficiency. Some even schemes overestimate their energy consumption and their efficiency is above 100%, which is not possible. Okay, so they have compared with policy 5. What they have seen is that policy 5 overestimates the video uh, the download related energy consumption. It always overestimates that, while the game related the application which is taking a lot of GPU power, it's underestimating that value, because the reason is that policy 5 does not take GPU as a hardware resource. It does not take into it takes only like GPS, CPU, and all these kind of major resources in accounting for energy. It doesn't take GPU as account, so therefore it's underestimating the game energy consumption. While if you see S, its game consumption is very high. So it has some advantages over policy 5 and it also has some limitations. As you can see, it does not assume any linear relations between energy consumption and resource usage. The thing is, it doesn't even, it's not, this energy accounting is not built on top of resource usage. So basically there is no linear relationship in that. And it's also easier to improve. If you want to improve policy 5, you have to look into more deeply into different kind of hardware resources. It's not easily improved. Whereas you can improve the accuracy of ES by, let's suppose, taking more measurements, more or less time period, for example. The limitation for this is that any software activity that cannot be timed, it cannot basically estimate the proper energy for that particular software. It's taking that time interval, very small time interval. The example is non-blocking I operations, and the other is that it's like a model-based approach. Mostly it's built on Shapley value model, and it is estimating a lot of statistical averages, which I've shown you in the table, when it's taking the hardware resource state into account. And like I mentioned, it's blind of resource usage. It's built on a separate model. At the end, you don't know that this much energy this software principle has belongs to which resources are actually contributing to that energy. And the conclusions are, they say that Shapley value is the ground truth for energy accounting, which I think is only the theoretical version is the ground truth, not the approximate version which they proposed. And they say that it beats all the previous policies, even the state of the art policy 5. And it's like interdisciplinary research, which is awesome. Thanks.
Thanks. So, any thoughts on this? Those of you who were quiet today, any comments? Back there? No? Intrigued?
I feel like those hardware states might be very variable. Like, it's very specific for the evaluations they did, but I don't know if it will work as well for other devices. And also, since it's not implemented in the phone, integrated, I don't know how accurate this chapter is. They work well here.
So that's trying to solve a very hard problem. If you kind of reflect about this thing, right? So essentially, so this is a problem in context of like buildings and building energy and all is called apportionment. Okay, so basically idea. So let's say in your home, you have a family, multiple individuals. We all consume energy doing different things, different lights, fridge, stuff like that and all. And we want to basically, let's say, assign ourselves our carbon footprint, personal carbon footprint. This kind of has been in vogue. How now, even if, let's say, you had the ability to measure individual subsystems, your fridge, your light and all, even then it's a hard problem, because certain resources are inherently resources whose power consumption is not additive. So what I mean by that is let's imagine, say for the sake of argument, the printer in my lab. Okay, so it sleeps when no one is printing it. When someone sends a print task, it wakes up, prints, stays on for some time, goes back to sleep. Now, often what happens is a person sends a task to print, the printer wakes up, there is a waking up energy, then the printing energy, then idles for a while, and it goes back to sleep. If that's all it did, one task, it was an isolated wake up, print, go back to sleep thing, I could apportion the energy nicely. Now, what happens if a second task followed right during that wake up moment? Now suddenly your apportionment, that overhead part of the energy, one would argue that fairness probably says that they should be divvied up in some proportion to that sort of thing. The same thing which happens in a computer, right? I mean, are things like radios and all. When you send when one app sends a packet, the radio presumably wakes up and all using kind of driver-based wake up and all that we kind of heard previously, and then it goes back to sleep. But meanwhile, if a second packet was sent by some other application, it's not as if they are just adding up. So even if we had the entire ground truth, the reality is we don't actually have all the ground truth either, which is why kind of a very common way these things are done is that you look at indirect indicators of energy consumption. So you would say it stands to reason number of memory access, number of packets sent, number of cycles executed. We expect each one of them is probably going to have some monotonic and usually linear relationship with the overall power consumption, and we kind of do that. But the problem is that if I sent n packets and another application sent n packets, then there is the radio is also consuming energy at times when we were not sending this packet. Worse, sometimes we do things which the system does on our behalf at a time when we are not running. What I mean by that is an application may actually be inactive, but the OS may be doing stuff on its behalf at the time, like actually receiving a packet or doing a disk I/O, which again we don't keep track of. So it's a very hard problem. So ultimately, one thing to realize that even this work, which is looking at what application was running in any given snapshot and all, is not tracking some of the issues that I'm bringing out, which is what if the OS was the one running and doing some stuff on behalf. So hard problem, but I guess what the nice thing about this paper is it's basically kind of seeking to answer what, in the absence of this information, which fundamentally we can never have, what stands for a very reasonable way of apportioning, and that's where the 4 axioms kind of come in, and that any solution should have some properties hold true, and they're kind of approaching it from that perspective. So kind of nice thing on that perspective, but it's an impossible problem. Okay, you can instrument to whatever extent you want, but you would still not be able to come up with something you would say which is the answer for this particular problem. But at the same time, apportionment is something that sounds attractive. Like, for example, you might imagine that we might price based upon the energy you are consuming, because we kind of talked about that, how power consumption in some cases is part of the runtime cost, or maybe simply that you want to motivate changes in behavior. So it would be good to be able to apportion correctly in those cases. So useful thing to have, being able to apportion, partition, assign blame for energy usage, but it's kind of a hard thing to actually achieve. And even these guys, I mean, they're treating their work as the ground truth, but that in itself is something to question. Any other insights? Okay, so remember, this Thursday we don't have a lecture. We are going to do the makeup on Friday. So I'll send out a reminder again.